Hi, my name is NURUL ZAWANI, so I will briefly explain and introduce about HPLC. So, in the recent years of the technology which has been used in chromatographic analysis, it has been greatly improved as there is an existence of high-performance liquid chromatography, which is as shortened known as HPLC. These devices allow very efficient separation of the small amount of components that could be found in a mixture. So, this technique is essential and it works the same as the liquid chromatography. However, the results obtained are known to be more accurate and effective. It has efficient feature as the column in HPLC, it has very tiny diameter, which is 5 micrometer for the diameter, where this allows the large surface area to absorb each of the molecules. Therefore, this particle can be considered as stationary phase of the chromatographic system. Since the tiny particle has tightly and packedly arranged, the mobile phase solvent will be go through the column by the force where with the aid of high pressure. So a detector and a computer are also need to be connected to the HPLC instrument in order to signal where the eluents are coming off the column and the fraction should be collected. In this experiment, there are few objectives, which includes this experiment is done to determine the retention time of the standard solution, the one that we will be using are caffeine. Secondly, to identify the caffeine pill in a soft drink sample, which we will be using Coke. And thirdly, is to determine the amount of caffeine in soft drink sample using the response factor method.
In this methodology, there are two key detectors, which are DAD as well as RAD. DAD stands for diode array detectors, whereas RAD stands for refractive index detectors. So each step in this process is interconnected to ensure smooth operations as well as reliable results. The process begins with sample preparation, where the sample is filtered, diluted, or sometimes adjusted to ensure compatibility with the HPLC system. This step is crucial because a clean and well-prepared sample avoids clogging the system and ensures accurate detection. For DAD, the sample must contain compounds with UV visible absorption properties, which might require pre-treatment like derivatization. Whereas for RID, it is essential to remove particulates and avoid solvents that could cause refractive index fluctuations. Next is instrument setup, where the system parameters such as flow rate, column type, and temperatures are carefully optimized. The choice of mobile phase is especially critical at this stage. For DAD, UV transparent solvents like water, methanol, or acetonitrile are ideal to prevent interference during detection. Meanwhile, for RID, the mobile phase must have a stable reflective index, as any fluctuations can lead to baseline instability. By ensuring the setup aligns with the needs of both detectors, the system is primed for consistent performance. Following this, the mobile phase preparation comes into play. The mobile phase must be prepared with high purity to avoid contaminations and noise in the chromatogram. For DAD, it is crucial to select solvents that do not absorb in the UV range, as this ensures clear and reliable absorbance measurements. On the other hand, for RID, the mobile phase must be stable in the refractive index to avoid signal fluctuations. These careful preparations ensure seamless interactions between the sample, mobile phase, and detectors. The prepared sample is then introduced into the system through sample injections, where precision is the key. Accurate injection volumes prevent oversaturations for DID, ensuring clear and consistent absorbance data. For RID, uniform concentrations are necessary to maintain a stable and reproducible signal. This step directly impacts the accuracy of the data collected by the detectors. The prepared sample is then introduced into, and once the sample moves through the system, it reaches the detections and data collection phase. The DAD captures UV visible absorbance spectra across multiple wavelengths, making it ideal for analytes with chromophiles like aromatics or conjugated compounds. It provides both qualitative data such as spectral fingerprints and quantitative data like peak areas. Meanwhile, the RID measures changes in the refractive index between the analyte and the mobile phase, which is especially useful for compounds like sugars or alcohols that do not absorb UV light. Together, these detectors complement each other, allowing for a broader analysis of both UV active and non-UV active compounds. And finally, the collected data is analyzed during the data analysis step. For DAD, spectral data is used to confirm the identity of compounds, while peak areas help in quantifying them. For RID, retention times and peak heights are analyzed for universal detections of analytes. By combining the results from both detectors, a comprehensive profile of the sample can be obtained, covering a wide range of compounds with diverse properties. The Hplc system consists of several key components arranged in a logical order to ensure efficient operation. At the very top, we can see there are the solvent bottles, which contain the mobile phase required for eluting the sample through the system. These bottles may hold various solvents for gradient elution or washing purposes. Below the solvent bottles is the solvent delivery system, or pump, which pumps the mobile phase at a precise and consistent flow rate into the system. This module ensures the desired pressure for efficient separation, and gradient pumps can mix multiple solvents in specific ratios. Next, the autosampler is located below the pump. It automatically injects a specific volume of the prepared sample into the system for analysis, reducing human error and increasing reproducibility. Centrally located in the system is the column compartment, which houses the analytical column and maintains a stable temperature. This is the critical sections where the separations of sample components occurs based on the interactions with the stationary phase and mobile phase. The detector modules are positioned below the column compartment. These include detectors like DAD, which measures UV visible absorbance across multiple wavelengths to provide qualitative and quantitative data, and RID, which measures the refractive index of the eluent for non-UV active compounds like sugars or alcohols. Finally, at the bottom of the system are the waste and data processing units. The waste port collects used mobile phase and eluted light, which the data processor, usually a connected computer, processes signals from the detectors and generates chromatograms for analysis. Together, these components enable the Hplc system to provide seamless workflows for sample preparation, detections, and analysis, ensuring accurate and reliable results.
This table shows us the results of the HPLC reading that we have obtained from this experiment. We use three types of compound. The first compound is the caffeine standard. The retention time that it has is 2.482 and the peak area of the caffeine is 6249.48779. For the soft drink sample 1, we have analyzed the cough drink. The retention time that it has is 2.481 and the peak area of the caffeine is 7001.12305. For the soft drink sample 2, we have analyzed the Levita drink. The retention time that it has is 2.019 and the peak area of the caffeine is 3.48617 times 10 to the power of 4. After we obtain the retention time and the peak area reading, we have to calculate the concentration of the caffeine in ppm for the soft drink. In order to do that, we need to use the two types of formula, which is the response factor and the concentration of caffeine. So, before we proceed with the calculation, we have to calculate the RF first. So, as we can see, the conversion factor here is 1 mg per ml equals to 1000 ppm. So, to calculate the RF, we have to put the value of the peak area of the caffeine from the table, which is 6249.48779, and then we need to divide it with 0.1 mg per ml, and then we got the answer 62494.8779 mg per ml. After we calculate this, we can proceed with the calculation of the concentration of the caffeine. After we obtain the RF value, we can now proceed with the calculation of concentration of caffeine. In order to do that, we need to use the second formula as I mentioned before, which is the concentration of caffeine equals to peak area of caffeine in sample and then divide it with RF. So, in order to do that, we need to take the value from the peak area of caffeine for soft drink sample 1 and then divide it with the RF value. And the outcome that we have is 112.027. Same goes to the sample drink 2. We use the same formula, we use the same step also, and then we obtain the peak area of caffeine value and then divide it with the RF value. The outcome from the calculation is 557.821 ppm.
Hi, my name is ASSHARIMAN. Today we will discuss about our discussion. From our result, the Hplc analysis successfully quantified the caffeine content in the standard sample. The retention times for both soft drink samples are 2.481 and 2.019 minutes, whereas sample 1 is very close to retention time of the caffeine standard, which is 2.482 minutes. It indicates that the sample and the standard compound are likely eluting at similar times, suggesting that they have similar chemical properties such as polarity, molecular size, or affinity for the stationary phase. The peak area for the soft drink samples are 701.12305 and 34,861.7. They are significantly different, indicating a substantial difference in caffeine concentration between two samples. The response factors RF is calculated using the peak area of the caffeine standard, and it's known as concentration. The provided conclusion shows a response factors of 62,494.8779 mg/ml. The corrected solution used the provided peak areas and the seemingly corrected response factor as the calculated in the result. Round 1 caffeine concentration is 127.027 ppm, while the second result of caffeine concentration is 557.821 ppm.
So the conclusion is the objective of the experiment were achieved. The caffeine standard exhibited a retention time of 2.482 minutes, while the soft drink sample showed retention time of 2.481 and 2.019 minutes, confirming the presence of caffeine in the samples. High performance liquid chromatography, which is Hplc, will effectively separate, identify, and quantify caffeine in the samples. The response factor, defined as the ratio between the concentration of a compound and the detector's response, was instrumental in accurately determining caffeine concentrations. Hplc's precision and sensitivity make it a reliable tool for analyzing complex mixtures. In future studies, Hplc can be utilized for detecting impurities, analyzing additional compounds, and enhancing quality control in industries such as food, beverages, and pharmaceuticals.